Assalamu alaikum. Hello students. Today we have to solve problem number 2.6 of Electrodynamics 4th edition by David J Griffiths. In this problem we have been asked to find electric field at some point P at a vertical distance z from the center of a circular disk carrying uniform charge density sigma. And now in this case this is uniform surface charge density sigma. Okay, and the radius of this disk has been given as r. Now how can we find our required electric field at this point? For this purpose we will divide this complete disk into concentric loops. Then we will find electric field at this point due to one of those loops. And finally we will integrate that electric field due to a loop across this complete disk to find our required field at this point due to this complete disk. Now let us see one of those loops. Let's say this one is our loop. This one is our loop, like this one, and the radius of this loop is named as x. Okay, now the radius of this loop is named as x, like this. So this is the radius of our loop, okay, and named as x. So the width of that loop will be, so this is the width of that loop, and this width is taken as dx. Okay, now we have to find electric field at this point due to this loop, and the expression for electric field due to a loop we derived in our previous lecture in problem number 2.5, and that expression for electric field due to a loop came out to be this. So here in this case we will modify this expression of electric field for this loop, and that electric field will become, so the electric field due to this loop will be named as dE. That electric field will be named as dE because this loop is now here in this case is actually the electric field produced by this loop here in this case will be actually the elementary electric field, the electric field due to a charge element. That's why that electric field will be named as dE. Okay, so the electric field produced due to this loop element is named as dE, and that will be equal to, by using this expression, that will become kz dq. Okay, kz dq divided by z square plus x square, because in our previous lecture we derived electric field due to a loop, and in that case we taken the radius of that loop as capital R. But here in this case the radius of this loop element is taken as x. That's why here this r will be replaced by x, so it becomes z square plus x square, and whole power 3/2 is written here as it is. Okay, so this is our electric field due to this loop element. Now we want to find electric field due to this complete disk at the same point. For this purpose we will integrate that electric field across this complete disk. Okay, so let's integrate. So if I integrate the left hand side, it becomes the complete electric field E. It becomes the complete electric field E due to disk. And at the right hand side we know this k is constant, so will be written outside the integral. Z is constant, so written outside the integral, and this dq will be written inside the integral. Dq divided by z square plus x square whole power 3/2. Again, we have two variables inside the integral. The first one is q and the second one is x. X is also variable because we know that if I take this loop of smaller size, then definitely the radius x will be smaller, and if I take the loop of larger size, then its radius x will be larger. That's why x is also a variable here in this case. So we have two variables q and x inside the integral, but we know by the rules of mathematics, to integrate this expression should contain only one variable. So we will transform this q variable into x variable. We will convert this q variable into x variable. So if I convert this q variable into x variable, I will use here the expression like we know that this sigma is charge density, that is q divided by a. So if I use this charge density for this loop, I will write something like this. Sigma is equal to charge contained by that loop divided by area of that loop. Now what will be the area of this loop? Definitely its area will be equal to its length, that is 2 pi x. Its length, that means its circumference, 2 pi x, multiply its width. What is its width? Its width is named as dx. So multiplied by dx. Okay. Now if I separate the value of dq from this expression, that comes out to be like kz, and now the value of dq from this expression becomes 2 pi x sigma into dx divided by z square plus x square whole power 3 by 2. Okay. Now once again, these terms 2 pi and sigma are constants, so will be taken outside the integral. So I'm writing those terms outside the integral. 2 pi and sigma, these were the constant terms, so written outside the integral. Okay. Now inside the integral we have just like x and dx. Now we should also have the limits of integration. So what will be the limits of integration here in this case for x variable? That's pretty clear that x is actually the radius of this loop. So if I take this loop of 0 size, then x will have lower limit as 0. But if I take this loop at the edges of this disk, then definitely in that case the radius of that loop will be equal to the radius of the disk. Okay. So the upper limit is taken as r. Hope it's clear. Now let's integrate this expression. We are well aware for integration, let me write the expression first. K z pi sigma, and now where is 2? Let me tell you. Now if I shift this denominator, the expression in the denominator upwards, it becomes z square plus x square whole power minus 3 by 2, and that x in numerator is written as it is. Now dx. Now to integrate this expression, we should have the derivative of this expression here. Now what will be the derivative of the terms inside the bracket? Its derivative will be 2x, but here we have just x. So to complete its derivative, we shifted this 2 inwards. Okay. So this is that 2. Now it's easy to integrate it. Its integration becomes like z square plus x square whole power minus 1 by 2 over minus 1 by 2, and the limits of integration are 0 to r. Now in the next case it becomes like minus 2 k z, this one is 2, okay, minus 2kz pi sigma, and it becomes 1 over z square plus x square inside the square root from 0 to r. Now if I apply these limits of integration, it becomes 2k z pi sigma. So if I apply these limits of integration, it becomes like 1 divided by square root of z square plus r square minus 1 divided by z square plus 0 square, and that finally becomes 1 by z. Okay. Also, if multiply this negative sign inside the bracket, then definitely both these terms will change their position. So here it will become 1 by z, and this one will become like 1 divided by z square plus r square, z square plus r square inside the square root. Okay. Now this is the electric field. This is our final electric field due to this complete disk at this point P. Now let us discuss those two special cases have been given in the statement of this problem. The first special case is what will be the electric field if R approaches to infinity. If R approaches to infinity. Now we have to find electric field if R approaches to infinity. That means if this disk becomes of infinite size, then what will be the electric field at this point P? So let us calculate, because I have shortage of space here, I cannot complete it here. So I'm gonna remove this one, and then I will calculate for that special case here at this space. Okay, now let us discuss that special case, and the electric field I've just calculated is written here now. Now the electric field in this special case when R approaches to infinity, that means if the radius of our disk becomes infinite, if the size of our disk becomes infinite, then in that case the electric field will be 2k pi z sigma 1 by z minus, and then by taking r square common from inside and then bringing it outside the integral, it becomes 1 by z and square root of z square by r square plus 1. Okay, sorry, that was r, not z. Now in the next step it becomes 2k pi, because we took r square common here. Okay, we took r square common here and then brought it outside the square root, so outside it becomes r with power 1. Now 2k pi z sigma 1 by z minus 1 by r, and then it becomes 1 plus z square by r square whole power minus 1 by 2, whole power minus 1 by 2. Now in the next step it becomes 2k pi z sigma 1 by z minus 1 by r, and then by applying binomial expansion here on this bracket, it becomes 1 minus 1 by 2 z square over r square plus neglected terms. Okay, all the higher powers have been neglected. Why? Because r approaches to infinity. R is very, very large. So in higher powers, definitely higher terms will contain higher power of r in denominator. That is in the next term. The denominator will contain r power 4. Okay, and definitely that term will be ignored, that term will be neglected, because if in denominator r has higher powers, then denominator gets larger and larger. and in this way our this complete term, that complete fraction will be removed. Okay, hope it's clear. Now it's pretty clear that r approaches to infinity. So if I put here r infinity, this term will be 0. Okay, this term will be 0. This term will be 0, and then when 0 will be divided by this bracket, that bracket will also be removed, and we are left with only 2k pi z sigma 1 by z, and all those terms have been removed, so minus 0. Okay, now in the next step it becomes 2, and this k, we know it's Coulomb's constant, so it is 1 by 4 pi epsilon naught. Okay, pi z sigma, pi z sigma, and now finally 1 by z. Again z and z have been cancelled out, z and z have been cancelled out, pi and pi have been cancelled out, and finally it becomes what? Sigma over 2 epsilon naught. So this is our final electric field in that special case. In what special case? When our disk becomes of infinite size, when its radius becomes infinite, then in that case the electric field at that point P due to this disk will be like this. Do you know what does this expression tells us? This is actually the expression of electric field due to an infinite sheet. That means if this if the radius of this disk becomes very very large, then in that case that disk will behave like an infinite sheet for this point P. Okay, hope it's clear. Now let us discuss the second special case, the special case in which this z distance becomes very very large as compared to this r distance. Now let us discuss that special case. Okay, now let us discuss this special case in which z becomes very very greater as compared to r. That means this point P gets very very far away from this disk. Now let us see what will be the electric field in that case. So again this expression can be modified as 2k pi z sigma 1 by z. Now in this case z is very very large, so that's why here in this case now this z square will be taken as common, and then will be brought outside the square root. So finally it becomes 1 by z, and then square root of 1 plus r square divided by z square. Okay, now by taking this z common from denominator and then cancelling it out from this z, it becomes in the next step like 2k pi sigma 1 minus 1 plus r square plus z square whole power minus 1 by 2. Again we will apply here binomial expansion, and then we will get 2k pi sigma 1 minus, now by applying binomial expansion on this expression, it gives like what? 1 minus 1 by 2 r square plus z square plus neglected terms. Again neglected terms. Why the higher terms have been neglected? Again the same reason, that z is very very larger than r. So in the next terms, in the higher terms, we will have z with higher power in denominator. As the z has higher power in denominator, So that means our that fraction is getting smaller and smaller and finally have been removed. So the higher terms have been removed because they have higher power of z in denominator. Okay, now by multiplying this negative sign into the bracket, we know both these terms will be cancelled out, and we are left with 2k pi sigma, and it becomes like r square divided by 2z square. Okay, r square into 2z square. Again this 2 and 2 cancelled out, and it becomes k pi sigma r square divided by z square. Now what does this expression gives us? The expression like this one, this expression. What does this expression gives us? It's pretty clear that the radius of the the area of the disk is pi r square because it is a circular disk. So this expression can be written as like this: sigma is equal to k divided by pi r square. Okay, pi r square, because this expression of uniform charge density was written for this complete disk. So that's why that was the charge of the disk and that was the area of that disk. And the disk is circular, the disk is in circular form, so area of that circular disk will be pi r square. Now by separating the value of q, it becomes sigma pi r square. Now it's pretty clear that this expression sigma pi r square gives the complete charge of that disk, so it becomes k q divided by z square. So this is our final electric field due to that disk in this special case. What special case? When distance c becomes much larger than r. That means when our point P gets very far away from that disk, then in that special case the electric field comes out to be this. Now again, what does this electric field tells us? What does this expression tells us? This expression tells us that again our disk is behaving like this disk is behaving like a point charge for the point very far away from it. Okay, because we are well aware that this is the expression of the electric field for a point charge. Hope it's clear. In the next lecture we will discuss problem number 2.7. Goodbye.